Hello everyone, welcome to Statistical Foundation for Big Data Analysis. We continue with our second module on statistical learning theory. Today's topic is methods of cross-validation. In last class, we discussed the need for cross-validation in statistical learning theory because ultimately what happens in real life is that you are given a specific data set. You are given just one single sample, and based on that one single sample, you have to do your analysis. In theoretical discussions, we talked about bias variance decomposition, etc. But all those calculations, total error, bias, variance, all those theoretical calculations assumed that you have information about population. If you know about the population for this particular population and let us say a particular type of algorithm, you can give a good understanding, you can draw good insight about what will be the bias, what will be the variance, etc. But in real life, you do not have information about the population, because after all that is what you are aiming at, like you are trying to learn about the population from the sample. So, you start with a sample, and in most cases you are stuck with that. And also there was another aspect for calculation of bias, variance, etc. We were taking average over all possible sample. Forget about all possible sample, which may just be theoretically impossible to draw because it may just be infinite, but even drawing large amount of samples, which we actually did for giving you some examples of empirical computation of bias and variance in last class also, drawing large amount of sample, that itself may be forbidden. You may have to just work with one sample. So, you have to use that sample to build the model, and that is it. So, if the model is good, it is good, if it is bad, it is bad. So, there is really a need for a method based on the sample itself, using which you can judge the efficiency of your model, your algorithm. So, there comes this cross validation technique. We saw this test set, training set, this method of breaking the sample into training set and test set and building the model based on the training set and testing it on the test set. We saw this framework in last class, and this brings us to this arena of cross validation. So, very loosely speaking, the philosophy of the cross validation is to use the sample itself for training and testing. So, of course, if you just split the sample into two parts, train it based on one part and test it based on another part, it is essentially like inferring about whether what is the head probability is based on 1 toss or 5 toss, and let us say test that on another 3 toss. So, lesser this number of these number of tosses are, less reliable your inference will be. Now, what do you do? If you are stuck with that, what do you do? So, there are various cross validation techniques that we are going to discuss today, which will actually reuse the same sample in various different ways to treat it as different samples. This assumes the sample is random enough and a representative of the population. So, it manipulates the same given sample in various different ways to treat it as various samples, and does this cross validation based on test and training split of those various samples constructed out of same sample, and takes the average training error and average test error, and it is believed that that sort of gives you a reasonable idea about how good your model is. It is like the I mean, in India we are always in this election mode, like there are exit polls after every election, but you must have heard this word called poll of polls. So, generally speaking, the idea is that even if one particular exit poll gives you wrong prediction, poll of poll tends to give you the correct direction. So, this is sort of the idea. So, now let us get into the specific methods. So, first is let us just recall quickly the cross validation setup. You have this full data I running from 1 to n, x I, y I. You are building a rule for predicting y based on x, HS based on a particular sample, in this case is this given data, and you have this loss function. Now, I am using this general term loss function because so far so this is basically measure of the difference between actual and predicted. This is written in a rather general philosophical term, but that's it. I mean, we so far saw this loss functions to be this average loss of predicted minus expected. Like for example, difference between HSX minus expected value of y given x, you take the square, you sum it over all possible x and all possible, you average it over all possible x and all possible s to get the bias. If you average it over all possible s, all possible x and all possible y also, that gives you the average total error. But this squared difference between predicted and actual need not be your only measure of difference. There can be other measures of difference. One absolutely crude measure will be if you see that HSX, that your predicted, is exactly equal to expected value of y given x, then you call it 1. If it is not equal, you call it 0. That's 0 1 kind of prediction. Either it is perfectly equal or it's not equal. So every kind of not equal, you give them same degree of negativity, degree of failure. So either it succeeds completely or it never succeeds. Or another thing can be, you can define that if the difference is between you can stratify it, like difference between 0 to 10, you can tell it 1, you can give a number 1. If it is between 10 to 20, you give it 2. You can do all sorts of difference measures, but some measure of difference between predicted and actual, that's your loss function. And the risk estimate is basically over the training sample, calculate the loss functions, all the training data points, you calculate the loss function and divide it by the size of the training data. By the way, for any set S, mod S denotes the size of S. So this is something you remember. This is a standard mathematical notation. Like if set 1, 2, 3, 4, 5 has size 5, set 1, 2, 3, 5 has size 4, and so on. So general form of the loss function, as we are saying, is just for a general data set, is just you calculate it on the whole all the data points and take the average of it. So generally speaking, lower the loss function is, better the prediction is. That's the underlying philosophy. So this is your squared loss function that we discussed. This is used in regression also. Another loss is considered to be this logistic loss. This we will explain in detail in next class. This is closely related to something very important we studied earlier, namely the maximum likelihood estimation. So this has something to do with likelihood. So minimizing logistic loss is something similar to maximizing the likelihood. So it's basically negative of the likelihood. So for something to happen, to estimate some population parameter, you remember you were looking for the value which maximizes the likelihood. There were two aspects, two approaches we saw so far. One was for this ordinary least square, you are looking for the population parameter which minimizes this least square error. So minimizes the loss, that's one approach. Another was maximum likelihood estimator, where you were looking for maximizing the likelihood, the parameter value which is maximizing the likelihood of the observed data. That was the maximum likelihood estimator. Logistic loss is basically, it's a loss function which is defined to be negative of the likelihood. So maximizing likelihood is same as minimizing the negative of the likelihood. So this is what logistic loss is. In fact, you will see in case of when we do linear regression in detail for normal population, when you are doing linear regression, when you get the least square estimate, the Gauss-Markov estimate so called, that is something which is both least square estimate, that is minimizes the this squared regression loss or the square distance loss, as well as that's also a maximum likelihood estimate. So that also minimizes the likelihood loss, or which is sort of related to this so called logistic loss. We will get into this in details, not the regression part, that is for the next module, but logistic loss we will discuss in details in next class when we discuss logistic regression in the context of classification. Another loss is of course this 0, 1 loss, which I just said. You define it to be 0 if y equal to hx, that is no loss, or always 1. Every other, whenever it is different, you define the loss to be 1. So, these are some common examples of loss function. So, now we just have the same setup as we discussed earlier. You split the sample into two parts, test set and training set. You train the model based on training set and test it on the test set. You see measured the loss function on the test set. So, the key idea is that like single split provides a fast method. So, this when you the general framework we discussed earlier, it's given a name when you are just simply splitting it into two parts, just splitting it into one training set and one test set. It's called the holdout method basically. It's called, the name for this most basic method is called holdout method. The advantage of this method, as you can see, this has many disadvantages. We just discussed a moment ago that like this is akin to just simply judging head probability based on results of 5 toss and testing that result on 3 more tosses. It is very unstable because number of observation is low and also very much dependent on those specific data points. But the advantage is that it is very fast. You do not have to do anything, you just have the data already, you just run the algorithm, done. It is a fast outcome. But as we can guess, this is fairly unstable. So, this is the mathematical framework of holdout method. You basically take the loss function on the average loss function on the training set, that is called the holdout risk. Like this is the training, this is the test error. You fit the model using the training data, test it on the test data by calculating this risk, the average loss function on all the test data points. So, generally speaking, it will be high variance because you are only testing testing this loss function based on one sample, one particular sample. You are not doing any so called resampling, which we will see in the other more advanced methods in a moment. Common split ratio is generally 70-30 or 80-20 as we discussed in last class. The next method is called so-called leave one out cross validation. From here we start methods where we actually tend to use the same sample multiple times, treating them as different samples and take the average over all those samples, trying to make up for our lacuna of having access to multiple samples or having unbridled access to sampling itself. So, we have only one sample we have started with. How can you use that sample as different samples? And so, this is actually a very central theme in cross validation, whether somehow once a drawn sample can be re-randomized to be considered as different samples. So, this is the first method. Here what you do, starting from one sample, you create, suppose the sample is of size n, you create n different samples. Here is how you do it. You pick up one point in that sample as your training, as your test data. So, test data set will just consist of one data point and the remaining part will be your training data, and you do that for every point. Now, if the sample is of size n, you get n such breaks. Now, you can treat n of these things as different samples, all n as different samples. Now, think carefully, you have drawn a sample randomly. So, each of the points are actually randomly chosen from the population. The remainder part of that is an IID sample. So, the whole thing is an IID sample. So, in particular, when you remove one point, remaining is also an IID sample of size n minus 1. Now, for each point the left out set is different, like if your data points are 1 to n, when you remove 1 you get 2 up to n, when you remove 2 you get 1, 3, 4 up to n, when you remove 3 you get 1 to 4 up to n, when you remove 5 you get 1 to 4, then 6 to n, and so on. Now, all these are different collections, so they are different sets of different IID sets drawn from the same population of xy, so they are different samples. So, this is how you end up getting n different samples, and each of them are split between n minus 1 size training set and size 1 test set. You do the training on this n minus 1, test it on that 1 point. Now, take the average test errors, average training errors, average test errors. So, the average of the test errors is your measure for the accuracy of the model. So, this is the mathematical framework of that. So, your basically your ith training set is S minus xi yi, ith test set is just single point xi yi, and you are taking this risk function, which is basically your loss function running from I equal 1 to n. You basically for each data, each sample, for the ith training sample, the test sample is of size 1. So, when you are doing the ith iteration of the process, ith iteration, your loss function, loss will just be, because there is only one data point, it will be just simply yi, that is the actual one, and then you have trained the data on the sample minus ith point. So, that is your model Hs minus I. You apply the Hs minus I on the xi, which is the x value of the ith data point, which is now your test point. Take the loss function between yi and that is your loss function for that training iteration. So, this is ith iteration. So, average loss. So, you call this, let us say, loss I, average loss will be, there are n such things, summation Li. This is exactly what is happening. So, this is nearly an unbiased estimator for general risk, because it is essentially the mean. You remember, the mean generally tends to give you unbiased estimator, but this has high computational cost, because you will almost do same number of iteration as the number of samples. So, if the sample is big, this is potentially, this involves high number of calculation. So, the k-fold cross validation is a generalization of leave one out cross validation. Here what you do, you divide the data into k different roughly equal parts. You use first k minus, so you divide the data, so suppose data sample is of size n, you divide it into k parts of roughly equal size. Out of those k part, in every iteration, leave one part out as test set, train the model based on the remaining k minus 1 part. Fit the model there, test it on this test set, calculate the loss function of that test, and then do it for every block amongst the k many blocks you have chosen. So, take their average. Basically, the repetition of the slight generalization of the previous one, where you are splitting there, basically k was n, because just and each of had size 1. Here, instead of taking n, you are reducing it to k, just to reduce the number of computation little bit. So, that reduces computational cost little bit, because you have to do it for less number of sample, but drawback is that also the number of sample gets reduced. But if n is sufficiently large and k is sufficiently large, that actually balances out. So, this is your formal method. You split the sample into k many different parts of roughly same size. Your jth training sample is S minus the sjth block, and the jth test block is just the sj. You calculate the, you train the model based on sjtr. So, that is your 8j, and then you test that on the jth one. So, calculate the loss function on that and take the average over all the data points in the jth block, and then take sum of all these errors. There will be k many such, because you are breaking into k parts, and take 1 over k. So, this is your k-fold cross validation. So, moderate computational cost compared to the leave one out. So, another concept is the stratified k-fold cross validation. It is more or less same, except that like classification data set having probably imbalanced classes, it's not homogeneous, it has different classes. So, then when you are breaking it into k parts, make sure that each part resembles the original data set, like it contains roughly same portion of all the parts there. So, perform k iteration, train on k minus 1 folds, test on the remaining fold, and average result across the fold. This is exactly same as the k-fold cross validation. Only difference is that you have to maintain that imbalance. So, if there is heterogeneity in the original sample, maintain that heterogeneity in each of the blocks. So that this becomes basically a fair representative of the sample, original sample. So, basically if NC be the number of samples in class n, so suppose there are different classes, then basically the number of, so if the original sample is of size n, maintain that like this proportion of class C in n in the original sample, NC divided by n, is maintained as much as possible in each block. So, in the jth class, jth block, the proportion of points from class C is same as the proportion of class C in the original whole sample. So, another thing is leave p out cross validation, choose a value p less than n. So, for every possible subset p of p samples, so this is basically, if you remember, this is NCP, which is n factorial over n minus p factorial over p factorial, also denoted by n choose p in some literature. So, these many possible subsets of p samples you can draw from n, and then train on remaining n minus p sample, test on p samples, and you do that for all possible p, and then take the average, all possible such samples, and take the average. So, this is your loss function. You are basically training sample is of size p, each training sample. So, when you are testing on n minus p fixed things, and that is your model S H based on S minus STE, TE is always size p, that is your model. You test that model on this test set, and then average it over the whole test set. What is the loss function? That gives you the loss function for a particular test set, like particular sampling process, but then there are NCP, n choose p many such things. So, you add all these, add this over all possible p combination, and take the average. That gives you the total or the average risk function for this sampling scheme. So, basically you perform the k-fold cross validation process on several times. Each repetition uses a new random partitioning of data, compute the mean and variance across all cross validation result. So, key idea is that repeating the process stabilizes the performance estimate and reduces the randomness. So, repeated k-fold cross validation is just slight variation of this. You perform k-fold cross validation multiple times with different random partition and average across all partition. If the process is repeated r times, you simply do it r times, take all the losses and take the average over r. So, this is useful when the data size is small, reduces the variance of k-fold estimate. Another thing is time series cross validation. When data is actually being calculated over time, there what you do, you take the previous data up to a particular time point as your training data, and the future data, like the data that is coming the last period, let's say it's 70-30 breakup, the first 70% of the time of the time instances you use that as a training data, and the last 30% you do it as a test data. This has a specific application in future forecasting, and secondly, you don't have to wait for the whole sample to be collected. Whenever your the required amount of training data is collected, you can start your analysis. So, it is very useful for future prediction models, where you are actually trying to predict what happens in future. So, this is the generalities of time series cross validation. It actually mimics the real life forecasting setting. We end our discussion here. So, I end the class here. Please stop.